Well, thank you, Ron, and thanks also to Merrick for arranging this, I think, originally. So yeah, I'm Jay Austin. I'm from the University of Minnesota Duluth, way at the western end of the Great Lakes system. And I'm going to give sort of a handful of little vignettes about ice and climate. And I'm going to say something to the students right now. One way to focus on a talk, and I do this regardless of the topic of the talk that I go to, is commit yourself to asking a question at the end of a talk. And you'll find you're trying to figure out what that question is. You might not end up coming up with one. But I often find that I get a lot more out of a talk if I decide that I'm going to ask a question at the end. I love the question and answer sessions in these. So please keep that in mind. OK, so I'm in a Department of Physics and Astronomy, which is a pretty typical thing. But I'm also at the Large Lakes Observatory. And I want to talk just briefly about what that is before we go on. So the Large Lakes Observatory is a group at the University of Minnesota Duluth. We all hold part-time, we have half-time positions in an academic department, and then a half-time position at Large Lakes. Our stated mission is the study of large inland water bodies around the world, the scientific study of them. And so there are plenty of organizations that study specific lakes. The Tahoe Environmental Research Center, for instance, studies Lake Tahoe, as you might guess. There are lots of Great Lakes institutes and stuff like that around the Great Lakes. And there are lots of places that spend a lot of time thinking about restoration or management of lakes, which are all very important things to do. We are focused on lakes around the world. So I don't remember who I was talking to about this, but we have projects. We have a very strong emphasis on the East African Rift Lakes. We have people working in Baikal, in Lake Matano in Indonesia, Lake Kivu, one of the gas lakes in Africa, high Andean lakes, looking at trace metals, dried lake beds in Mexico City. And so it's a very, very broad reach. And if there's interesting science that we can figure out a way to get ourselves there and funded to work there, we do it. So it's a wide range of lakes. And if there's a common thread that ties all of us together, again, I list all these different departments, is an interest in climate. And not just in our modern climate. I'm a very modern climate person, or at least the climate work that I do. It's not all that I do. But we also have a real emphasis on doing sediment core geochemistry, digging up cores from the bottoms of lakes, which end up being these fantastic tape recorders of the chemistry of the environment. And so we have, for instance, a core from Lake Tanganyika that goes back 600,000 years. And you can do geochemistry on that core to infer things about the past climate of the East African, of the African continent. So we're not all climate change people specifically, but we really are interested in how lakes are influenced by climate and how we can learn about that. My work at Duluth started thinking about climate. I've recently branched out into a lot of different things. The one thing I'm going to talk about today are ice characteristics and winter structure. One thing that you'll find if you look at the lake literature, and I don't know how many people in here are actually focused on lakes rather than some other aspect of the environment or of water or of physics, but we know very, very little about what goes on, especially in the Laurentian Great Lakes, the US-Canadian Great Lakes, the Canadian-US Great Lakes, in the winter. And that's because there are logistic challenges to studying them. On a small lake, you can take your snowmobile out and auger a hole and do science through the hole. If you're thinking about winter conditions in the world oceans, we have purpose-built research icebreakers that we take out in order to study the Arctic or the Antarctic ice sheet. But no such thing for the Great Lakes. You can't go out there. The scales are too large. The ice drifts around. We'll talk about that today. And so people are starting to really realize that there's this big gap in our understanding of these systems. Science doesn't stop just because the water's cold or because there's ice there. In fact, really interesting things go on. And so what I'd like to do is talk about what my lab has done to try to push that forward a little bit. I've also done some recent stuff. We got a provisional accept on a paper looking at these wonderful sediment plumes that come up the middle of, this is the western arm of Lake Superior. Maybe the geography isn't that familiar. Duluth, right here at the far western terminus of the Great Lakes in Superior, Wisconsin. So we're interested in the physical processes that are transporting the sediment offshore. We're getting really interested in convective processes in these large lakes. I've been doing some work on characterizing acoustics in the Great Lakes. In other words, listening to the lakes and seeing what they sound like, which sounds like a pretty abstract thing, and it is. It's just sort of fun right now. But there are reasons that we would want to have a better understanding of the propagation properties of sound in these lakes. And so we've got some side projects on that. And we do some more applied stuff. We're very interested in the Duluth Superior Harbor here, one of the most heavily anthropogenically impacted areas of the Great Lakes. And so we're doing some circulation modeling there as well. So a little bit of this, a little bit of that. Okay, so what I'd like to talk about today are, first of all, climate response and what I like to call seasonal connections. In other words, how does winter influence spring, influence summer? How does that information get propagated? How does that information get lost over time in these very large systems? I'd like to talk about some novel ice observations from the polar vortex winter 2013, 2014. If you were anywhere in the upper Midwest, you remember that winter. It was really an astoundingly cold winter, and we were lucky to have equipment in the lake over that winter, and we were able to learn a lot about the characteristics of ice on Lake Superior and in freshwater in general from that deployment. And then finally, I haven't put this into a talk before. We'll see how this turns out, but I think it's fun to talk about. And I talked a little bit about this with Kevin earlier today, Kevin Lamb, that there are still some really big sort of order one fundamental questions about ice formation on these lakes. And you might say, well, the lake gets cold and the water freezes. Well, yeah, but there's a lot more to it. And these systems don't behave like scaled up small lakes. We understand a fair amount about small lakes. These systems are really not just quantitatively, but qualitatively different. And so I want to talk a little bit about that. Okay, so just to orient you here, here's Lake Superior. Largest freshwater lake by surface area in the world, second, I think, by volume. 10% of the planet's surface freshwater in one space. Very heavily unpopulated. So Duluth Superior, right here at the tip, is the largest population center. Thunder Bay, which astoundingly is part of the same province, it just amazes me that I can spend that much time flying and still, be right next to Ontario. So there's Thunder Bay is the sort of the major metropolitan area on the Canadian side of the border, but relatively undisturbed compared to, for instance, Lake Erie or Lake Ontario, where there's a fair amount of agriculture within the watershed. So when I got to Duluth, and my background obviously is in oceanography rather than in limnology, the study of freshwater or inland waters. And I set about trying to find out something about just basic temperature trends in Lake Superior. And so I'm going to show a couple things from that era before getting into some of the more modern work that I've done. This right here, this is sort of astounding. Sault Ste. Marie, where Lake Superior drains into Michigan Huron, they have a power plant there. That power plant powers the locks that lift the boats from Michigan Huron up to Superior. And once a day, since 1906, an engineer measures the temperature of the water going through their power plant. For whatever engineering reason, you measure the temperature. But the point is, this is one of the longest time-resolved series of water temperature anywhere in the world. There's a temperature time series in Woods Hole, my alma mater, that goes back to like 1890, which is the longest. This is the second longest resolved. And we called up, and some of this data was already collated, but we were able to just, you call up and you ask the engineer and they send you photocopies, and we put this together. And you can't really see anything. All you're seeing in this particular plot is that it's warm in the summer and cold in the winter. So no great surprise there. But if you eyeball these maximum temperatures, you might convince yourself that things might be a little warmer than they were in the past. What we can do is look at summer average water temperatures here. So July through September averages at Sault Ste. Marie SSM. And then I'm plotting these in terms of anomalies. In other words, departures from some long-term mean. And here you can really start to see that there's really some trend. And with a little bit of filtering magic, we can convince ourselves that things really have warmed up quite a bit, especially since about 1980. So there does seem to be sort of a gentle trend here in the early part of the century, and then a plateau, and then really takes off since about 1980. This is the global air temperature average And then we can filter it as well, and it doesn't really call that different. When you're averaging lots of data together, typically you get less noise, and so we see a much smoother time series. We see sort of the same thing, a gradual warming, a plateau, and then a lot of increase since 1970 or 1980 in here. The funny thing is if we compare these two, and again, Lake Superior is a much smaller place than the whole globe, obviously, so we expect there to be a lot more natural variability there. But what you see is that the scales are very, very different. In fact, Lake Superior is warming considerably more rapidly than the global average. And there are lots of places. It's pretty typical. We would expect that perhaps from a mid-continent site. We would expect it from a mid to high latitude site. But the increase is really pretty dramatic, 1/10 of a degree Celsius, give or take, per year in this period. And obviously, fitting a straight line to that data, I think we would all take points off our students' papers for doing that. But the point is that this is a really rapid rate of warming. And I didn't actually characterize things in Fahrenheit like the introduction. I was surprised to hear that up in Canada. So we wanted to understand, first of all, is this just some weird thing that's going on in Sault Ste. Marie, or is this something that's more lake-wide? And so what we were able to do, this is sort of a busy slide. Here's Lake Superior, and these three sites marked WM for western, CM for central, and EM for eastern are the western, central, and eastern buoys that NOAA has been putting out since about 1980. All the Great Lakes have these sorts of buoys on them. This was a response, as I understand it, to the Edmund Fitzgerald disaster in 1976. Weather forecasts were very poor at the time, and in an effort to try to improve that, they started instrumenting the Great Lakes. They had been doing this in the oceans for quite some time before that. The point is here, so this top plot is Lake Superior, and here are three buoys. When we do that, we get numbers for the 1980 through 2015 period. I think this is actually 2014 here, which are, well, they're not a degree century per decade, but they're on that order of magnitude. And if we do the same thing in Lake Michigan with 2 buoys, Lake Huron with 2 buoys, we see stuff that's on the average of a 1/2 degree to 1 degree Celsius per decade with these, of course, these lines, which, again, we can have a long argument about that later. But the point is that things now are warmer than they were, say, 35 years ago. Okay. So in order to motivate the rest of this talk, I'm going to give you a short lecture on properties of fresh water and stratification. Some of you have already heard all this. Consider it a refresher. For those of you who haven't, fresh water is a really weird thing. Most of us are used to the idea that when we warm up a gas, it gets less dense. That's why we put hot air in hot air balloons. It's why on a hot day, the upstairs of our homes are warmer than the basement. That hot air wants to rise up to the top. Fresh water does that over here for temperatures that we're sort of used to. In other words, I increase the temperature, the density decreases. But below about 4 degrees Celsius, fresh water does the opposite. In other words, as I warm it, it gets denser. And there are complicated physical chemistry reasons for this that we're not going to get into, and we'll just leave it as a fact right now. There are fundamental consequences for freshwater systems, and especially freshwater ecosystems, of this weird arrangement of what we call the equation of state, or what determines the density, the relationship between density and temperature of this fluid. In the summer, if we go out into one of these lakes and we lower an instrument through the water column, what we would find is a layer of relatively warm water at the surface. And here, this might be 12, 15, as high as 20 degrees Celsius in Lake Superior. It might be 10 or 15, 20 meters thick. And then there's this big abyss of relatively cold water right around 4 degrees Celsius. And you notice that the density continues to increase. If you think back to that previous plot, the density increases with depth, which we expect. Lighter water has to sit on top of heavier water. In the winter, however, we can get what people often call negative stratification, in the sense that this colder water is going to sit on top of relatively warm water below. In this case, this surface layer tends to be very deep. In the winter, we have a lot of vigorous meteorological systems moving through that do a lot of wind mixing. And so we end up with a relatively thick layer of cold water sitting on top of relatively warm water below. So here, This is data from a buoy that we had out back in 2008, 2009. This is a one-year cycle of stratification at a site. I think this was our central site. It doesn't really matter. And each one of these individual curves is a little bit difficult to interpret on top here. Maybe make more sense down here. Each one of these individual curves is temperature that we measure at a specific depth within the lake. We can leave a mooring out. So we put one of these moorings out with sensors at various depths. We can leave it out there for 6 months or a year, recover the instrumentation, and then get the data out of the instruments. This bottom plot perhaps shows a little better. You can see the formation of this patch of warm water here through the summer and fall. It deepens over the course of time as wind stirs things up, and then starts cooling off here in the fall. It's isothermal for a month or two in the early winter, and then we get a very, very deep layer of extremely cold water here, and then eventually warms up. And you can sort of see these plots are redundant with each other. They just show sort of different aspects of that stratification. Okay, so this is sort of, if we were to look at water temperature at the surface at one of these sites, what we would see is slow warming here in the fall, in the spring, and it's slow because the heat that we're pouring in has to heat up the entire water column. And so there's a lot of water there, huge heat capacity, and we have to pour a lot of heat to get a small change in temperature. Once we form that layer of warm water at the surface, instead of pouring that heat into 150 or 200 meters, we're pouring it into the top 10 or 15 meters, and it heats up extremely rapidly. You can see right about where it reaches 4 degrees. We have this rapid increase, meteorological fluctuations and stuff through the middle of the summer, and then rapid cooling in the fall up until buoy recovery in November. I'm not sure why that slide's in there again. So the real question here is what drives when this overturn occurs. It doesn't occur at the same time every year. And in fact, there's a remarkable amount of variability from year to year in the timing of the onset of stratification. Oh, because this plot is different. This looks similar to that previous plot. What we can do is we can go out and grab large amounts of this temperature data from these buoys and look at when each one of these buoys reaches 4 degrees Celsius in each one of these years at each one of these sites. And there's not complicated, but there's a method for doing this in some sort of reasonable, high fidelity way. And what we see in every one of these sites, the 3 sites in Superior, 2 sites in Michigan, and 2 sites in Huron, is that the date that the lake reaches that stratification is getting earlier, consistently between all 3, 4, 5, 6, 7 of these sites. And on the order of sort of 3 to 8 days or so per decade. That doesn't sound like a lot until you think about the fact that, if we go back here, the lake only spends maybe 2 months warming up. And so if suddenly that onset of stratification is 2 weeks earlier, instead of 6 weeks of warming, we have 8 weeks of warming. And that's actually a significant difference, okay? And so one of the reasons that we observe these increases in summer water temperatures is simply because the lake's getting a head start. The lake is starting to warm earlier, not every year. Of course, there's a huge amount of interannual variability on top of this, which is a natural part of the system. But it begs the question, why are lakes stratifying earlier in this case, in these 3 lakes? To jump right to the punchline here, ice coverage. And there's controversy right now over whether ice is driving this or whether ice is heavily correlated with what is driving it. I'm not going to worry about that at this stage. Ice plays a role in the sense that, or the hypothesis is that, ice has a very high albedo compared to open water. If I form a layer of ice on top of the lake, a lot of the radiation that hits it, instead of being absorbed by the water in the winter and early spring, just gets bounced back out into space and is lost to the system forever. If that ice is not there, however, if there's less ice, then we expect more heat going into the lake earlier. The lake's going to warm up. And you can see here, each one of these dots is an individual year between 1980, I think, and 2014. And the higher this is a metric of ice coverage, which I'm not going to worry too much about the details of. You can see that the more ice we have, the later the lake stratifies. The less ice we have, like 2012 over here, we have very, very little open lake ice at all. And so the more, if we're taking ice away, and I'll try to convince you that that's in fact what's going on, if we take ice away, we would expect the lakes to we're going to be moving this way on this curve, and we're going to expect earlier stratification, and that's going to lead to warmer summers. And in fact, here's the last piece of the puzzle. This is the onset, that date of onset of summer stratification, and this is the summer water temperature. And you can see there's just a remarkable range from 6 or 7 degrees Fahrenheit up to about 18 for that summer average. So these are not small differences we're talking about. Admittedly, this is the range of variability with the natural variability on top. But the point is that we see a tremendous change or tremendous difference between a year in which the lake stratifies in, say, mid to late May and a year in which it stratifies in August. And so the really sort of fun result from this is that ice coverage determines a huge amount of the variability we see in from year to year in summer water temperature. So summer water temperature is certainly a function of whether we're having a warm summer or a cold summer, but it's also a very, very strong function of whether it was an icy winter or a mild winter the previous year. Again, 2014 continues to stick out like a sore thumb in some of these plots. In 2012, interestingly, just 2 years earlier, was a record warm year as well. Okay, so ice cover is in decline. Don't worry about the two colors here, they're just different data sources. But you can see that something's happened here in around 1998, and I still am not entirely sure. The climate system seems to have jumped the tracks in 98, and we're on some different route at this stage. But we see a lot of these sort of medium ice cover years here up through about 1998. And then after that, we have this whole string of relatively low ice cover years. 2009 was a pretty heavy year. And then 2014 over here is just this really remarkable year that I'll talk a little more about. And so there's this huge amount of variability from basically no ice at all in some of these years to very, very heavily covered. This metric, incidentally, is you look at the fraction of the lake surface that's covered on a day-to-day basis and then average those fractions over a specified time period to come up with that number. And so this, I think, is a really important question that we still have not entirely resolved, is why is this system so sensitive to small changes in climate? And I'm careful not to label these too explicitly. This is pretty vague here, right? Climate, ice. But it seems like we're somewhere on this very steep curve, and small changes are pushing us down into this region where we see little to no open lake ice. So a couple years ago, one of my grad students, looking at this plot, put this together. And if I was told that I was allowed to bring one slide, this is the slide, maybe the next one, but this is the slide that I would bring. This shows a lot of things. So, oops, I'm giving it away. So on this axis here is average air temperature in the winter. So December through May is admittedly a fairly liberal definition of winter, but we'll leave that for now. And then here's our average ice cover in percentage. And so here are the several messages to take home from this. First of all, 2014 was just an unprecedented year in the modern record. 2012, likewise, a really remarkable year. Almost all of these years right here, I should have color-coded these or something. Almost all of these years have occurred since 1998. So, except, of course, 2014 up here in 2009. But we've had a remarkable string of very low ice winters. And I think maybe the most important thing, especially for those of us who, at least part of our careers, are based around trying to communicate climate change to the public, these right here, and even these right here, are years with little to no open lake ice. So fringing bays will freeze and stuff like that. I'm talking about the open part of Lake Superior. And these right here, this cluster and everything above it, these right here are years where there's really robust ice coverage on the lake for at least part of the winter. And so you have people going ice fishing off of Brighton Beach in Duluth. You have people visiting the ice caves outside of the Apostle Islands. You have ships or boats, whatever, that either have to delay transporting ore or grain or whatever it is, or they try to and they get stuck. And so you have these cultural and commercial and recreational impacts of this ice cover. The difference between one of these very low ice years and one of these relatively high ice years is 1 to 2 degrees Celsius. And so that's really remarkable to me, that these relatively small changes in average climate state can actually lead to very large changes in what is a major portion of the sort of surface ecosystem of the continent. And I guess the other thing is, just for those of you who deal with real data, how tight this fit is. That's really sort of amazing to me. We can predict just about everything about this just by looking at the average winter air temperature. If I look at the other Great Lakes, we see very similar curves. There's an offset here because of depth. So Superior over here is a very deep lake. Erie over here is a very shallow lake. Erie is shallow, but it sits in a relatively warm climate, so it gets about the same levels of ice. These points that are separated from the rest of the plots tend to be 2014. Ontario here in blue is so deep and relatively warm and doesn't really form much ice. And so we can put a story together from all of this. We've shown that winter air temperature drives winter ice cover. Winter ice cover drives the timing of stratification. And then timing of stratification drives the summer water temperature. I didn't actually show that one, but that's in fact the case. And so what's really interesting about this is that it turns out that most of the variability that we see in summer water temperature in Lake Superior can be explained, about 60% in fact, up here, r² 0.61, can be explained with winter air temperature. And so there's a tremendous amount of connectivity there. One reason that's important is that one of the sort of common themes right now in climate change is that it's not so much that the whole year is getting warmer, it's that the winters tend not to be as cold as they were. And so a lot of the change that people are observing is in winter air temperatures. What this says is that, well, that's great, but that is going to affect Lake Superior in the winter as well. And it's worth keeping in mind that temperature, this water temperature, when it comes down to it, who cares what the water temperature is way offshore? Well, water temperature is this giant master control knob for ecosystems in these lakes. Small changes in temperature are changing metabolisms and nutrient uptake rates. Fish have specific temperature ranges in which they like to spawn. And so it's very difficult to make strong, reliable predictions about what changes in water temperature are going to manifest themselves downstream, so to speak, in the ecosystem. Okay, I'm going to switch gears, and I want to talk a little bit about ice on Lake Superior. Again, winter conditions, I feel, have been relatively understudied for the logistical reasons that I've suggested earlier. It's just really hard to get out there. Again, you can't take your snowmobile out. This right here is about 100 kilometers across. And so you're not going to walk or take a snowmobile out here safely. You can also see these big cracks and leads forming. This ice is drifting all around. And one thing that's really interesting about what we know about ice on Lake Superior is that we have very few direct measurements of that ice. There are not a lot of people, again, out there studying. George Leskovich at GLERL gets Coast Guard helicopters to fly him out here, and he lands on the ice, and they do a core or two, but that's an extraordinarily expensive way to study things. And so it turns out that most of what we know about ice on the Great Lakes, we know from remote sensing. So this is, I don't know what image this is, MODIS or something like that. And we take these satellite images, and then an analyst sits down and draws an outline around all this and says something about where the ice is and how much there is and how much it changed since yesterday and stuff like that. Not a whole lot about ice characteristics, basically nothing about ice thickness. And so there are all these really sort of fundamental aspects of ice coverage that we really don't have a good handle on. To give you a sense, this is a plot of ice coverage from 2005 to 2014. And while 2014 formed a little bit earlier than 9 and 10, the really remarkable thing is how late it lasted. There was ice on Lake Superior into mid-June, which is really remarkable. Not a lot, but the point is that it lasted very, very late compared to most years. To give you a sense of what that looks like on a seasonal basis, 2009, up until then, had been sort of our touchstone year for a heavy ice year. And you can see, so this is area percent coverage here. You can see that there was a period right at the beginning of March in 2009 where the lake was frozen over for a couple days. In 2014, it was frozen over basically entirely for 2 entire months, which is really pretty remarkable. To give you a sense of scale, here's 2012, that very, very low ice year. So there's just an amazing amount of variability from year to year here. In 2014, we had instrumentation under the ice that allowed us to look at a handful of different aspects of the ice. And I want to talk a little bit about that because I think this is, again, there's just nothing out there at this stage other than some of the stuff that we've done. There's some other groups that are starting to do some of this stuff. This is an instrument called an acoustic Doppler current profiler. It sends out pulses of sound from these transducers. That sound bounces off of stuff floating in the water column, phytoplankton or zooplankton or sediment or air bubbles or whatever, and then gets reflected back to the transducers. And there's a tiny little Doppler shift from the fact that the stuff is moving through the water column that this instrument can detect and then turn into a velocity. And it can do that at lots and lots of different layers. And it turns out, and I didn't really think about this until we got the instrument back, that sound is bouncing off the bottom of the ice as well. And so we can actually study the motion of the ice from underneath. So this instrument, I should point out, is in the water on a mooring looking up maybe 80 meters below the surface of the ice, sending those sound pulses out, reflecting back to the instrument, and recording the direction and speed of that ice sheet. And so here's a quick summary of this result. This is we found a wind station that was, we thought, reasonably regionally representative of the wind at our location. And so this is the direction of the wind. This is the direction of the ice. There's a fantastic, one of the very early results in observational oceanography. This is from Nansen back in the very early 1900s. He observed that icebergs drifted to the right of the wind. This has to do with the Coriolis force. It was really the birthplace or birth time or whatever of modern physical oceanography, is understanding the geophysical relevance of the Earth's rotation. And they observed that icebergs drifted about 20 degrees to the right of the ice. This right here says that ice on Lake Superior drifts to the right of the wind by about 20 or 25 degrees. And it's just sort of a fun result. I'm not sure exactly how significant. Here is the ice speed as a function of wind speed. And again, perhaps unsurprisingly, the faster the wind is blowing, the faster the ice moves. One neat thing, however, is that you can do some basic fluid dynamics scalings dealing with the drag that the wind imposes on the ice and the drag that the ice imposes on the water below. Make some very broad-reaching assumptions, and you can actually predict pretty well the ratio of ice speed to wind speed. This is the site at which we did this, here in the western part of the lake. It's maybe 50 kilometers or so, 70 kilometers to shore in the short directions. This is the ratio of wind speed ice speed to wind speed. And you can see that there's this weird sort of anisotropic distribution. In other words, that ratio tends to be a little bit longer along this northeast to southwest axis, which actually lines up with this axis of the lake. Again, we're able to measure the speed of the wind from this coastal station and the speed of the ice from our mooring site. In red is the wind speed, and then blue is the ice speed. In a lot of these cases, you can see that when the wind blows hard, the ice moves quickly, which is not a surprise. And when the wind dies down, the ice stops moving, et cetera, except there are periods like this right here, or here, or here, or here, where the wind is blowing like stink, but the ice is still. And what's going on there is the ice has stacked up against the coast. And when I say stacked up, I'm talking about stacked up against a coast 50 kilometers away, and has basically been frozen in place. And in fact, what you can do is you can use, the font didn't come out, don't worry too much about this, but the point is you can use information about the rheology of ice to make an estimate of what that ice thickness would have to be in order for the ice to be solid enough for it to not just crush together. This right here is a plot of wind speed, and in black we note the times when the ice is standing still. And so there are these times when the wind is blowing, which way does this go? I can't remember whether this is to or from. It doesn't really matter. The point is that when the wind is blowing, say, from the south, from the northwest, it can blow really hard and the ice doesn't go anywhere. And essentially the ice is all stacked up against that southeast coastline. This is when we put these moorings out, we put instruments called pressure sensors at 2 different depths on the mooring. And we do that so that when we recover the mooring, we know in retrospect what depth we put the mooring in at. We design it for a specific depth, but inevitably when you kick this thing over the side of the boat, it doesn't land in exactly 185 meters of water. It might land in 184, 183, depending on variability in the bathymetry. My favorite thing to do on these cruises is, for at least a couple of the instruments, take a look at the data right away. While you're out there, maybe you're steaming off to the next mooring or something like that. And I looked at the pressure sensor, and I saw all these huge spikes. And normally when you see that, you're like, ugh, the sensor, something went wrong with the sensor, and we're going to have to throw out the data, and we're going to have to get stuff recalibrated and stuff like that. But then I downloaded the second one, and I saw exactly the same spikes at exactly the same time. We also noticed in retrospect that those spikes tended to occur after ice on and did not occur after ice off in May. What was going on in this case was when 2 plates of ice crush together, they'll form a ridge, but they also have to form, for hydrostatic balance and stuff like that, they have to form a keel below. Imagine 2 giant plates of ice crushing together. All that rubble has to go somewhere. And it basically turns into this a ridge and a deep keel. And our mooring, as these keels passed our mooring site, pushed the mooring over, and those pressure sensors would be depressed in depth, record a higher pressure until the keel was passed, and then they'd pop back up. And so we'll go back to this slide really briefly. This is the profile of the deepest ice keel right here. Our mooring, the ball, the float on the mooring, was being pushed down as deep as 11 meters during the passage of these keels. So imagine 11 meters, that's give or take the height of this room, maybe a little bit more. There was that much ice there, and it actually takes close to an hour for one of these keels to pass. We were able to do an estimate, given the frequency and size of these, that roughly a third of the volume of ice on Lake Superior that winter was not in the sheet of ice, but bound up in ice keels of 6 meters thickness or more. And so from a thermodynamic standpoint, remote sensing is not going to tell you anything about the existence of these keels, but a huge amount of the volume of ice on the lake was actually in these otherwise undetectable ice keels. This is, I don't want to talk about this. There was sound. Ice makes noise. It makes noise at different sites. It happens at the same time. It got me interested in acoustics. I'm happy to go back to that. Again, I could give an hour talk on acoustics and be perfectly happy. What I want to talk about, though, briefly, is what I think is an outstanding problem in this field, and I think there are several people here that might enjoy thinking about this. Let's say that I cool down a lake to 4 degrees or maybe a little less than 4 degrees. If I take then a chunk of heat out of that water column, so the storm blows over and heat is removed from the lake, there are a number of things that can happen. If I have a mixed layer, that mixed layer can deepen, and then I have a lower heat content, that's fine. That mixed layer could cool, then we have a lower heat content, that's fine. Or ice can form. Any one of those three are completely legitimate things to have happen. I have a handful of different profiles from different experiments. I didn't do the Erie one, I guess I've done all the other ones. And the only difference between these two plots is the depth scale. These are little, lake is probably a rather vainglorious term for these. These are large ponds around Duluth that friends live on. And so they're 6 meters deep at best. And what you can see is that right below the surface of the lake, the temperature increases to, and there's some chemistry involved here, around 5 degrees. But the point is that basically what happened in these lakes is the lakes cooled and cooled and cooled until they reached 4 degrees. And then you get one bone cold night, and there's ice the next night. And once you form that ice, ice will just continue to form. Okay? And so that's true for all of these. This right here, St. James, is a deep pit mine lake in northern Minnesota. And you can see the same basic structure. Relatively warm throughout the whole water column. And then there's a good thick ice on top of this. On the other hand, the dark blue here is Lake Erie. The green is a coastal Superior site that I visited. The black is 2014, so this very cold year. And you can see that in Superior, 80 meters of water cools to about 0.1 degrees Celsius before ice starts to form. And once you get there, ice starts to form. The red is Superior in this very, very warm year. And you'll notice that you have a relatively well-mixed layer at about 2 degrees Celsius. And then at roughly the same depth, it starts to get warmer again. So in both of these years, the lake mixed and mixed and mixed to about 80 meters. In one case, it cooled all the way to 0 degrees and ice formed. And if you look at thermal structure at Western, Central, and Eastern, I think these are 2014, 13, 14. In each one of these cases, the lake cools down at the surface to right around 0 before you see any ice formation. So the dashed lines in each one of these cases is ice formation at these sites. Likewise, this is the same plot for Lake Erie, where you see it cooling and cooling and cooling, has to cool down to 0 before ice on, and ice leaves before you start to see it warm up at these two particular sites. And so I guess my outstanding question, the thing that I'd really love to see worked on, is what are the turbulent and mixing properties or processes that cause small lakes and large lakes to behave in fundamentally different fashions. The pathways to ice formation are fundamentally different in these two. The easy hypothesis, and I would completely agree with you if you told me this, is that these large lakes have a lot of fetch. You get big storms, you get big waves, you get lots of mixing. But for instance, why doesn't Lake Superior just continue to cool and get deeper and deeper and deeper? What sets this depth? What sets the 0.1 degree? There's a whole host of really interesting questions that I don't think are well understood surrounding ice formation on these lakes. So really quick conclusions. I thought I took that second one out. There's strong seasonal connectivity. One season determines the next. Winter conditions are a huge, important driver of summer water temperature conditions. There are likely to be ecological knockoffs from that. We've made a lot of progress, I think. We still don't have great ice thickness measurements, but I feel like we're making progress on these direct observations, leaving instrumentation in the lake over the course of the winter. And finally, I think that one of the really interesting questions to start addressing right now is understanding these pathways from fall conditions into the ice-covered season. So I'll stop there. Quickly acknowledge a lot of the open lake work is funded by NSF, also the Great Lakes Observing System, Sea Grant, and then my university. Daniel Tizzi is a PhD, was a PhD student of mine that did a lot of that ice characterization work. Steve Coleman worked with me, a fellow colleague at LLO, on a lot of the early climate stuff, and Catherine O'Reilly actually was head of that collaboration that I haven't talked about here, but would be happy to discuss in the questions as well. So anyway, there you go. Thank you very much. And so the trick So the question has to do with developing better. Let me broaden the question just a bit. Developing better platforms for studying these, being able to be out there either in person or autonomously. And so let me give you just a quick sense of where that is at. First of all, there are not research-dedicated icebreakers on the Great Lakes, whereas there are in the Arctic and the Antarctic. We do have icebreakers, but they're there for commercial use. They're to break pathways for colliers and ore boats and stuff like that. Those captains spend a lot of time looking for the path of least resistance. And so they're not going to where you want to go. I've been told, and I've gone and had lunch with the captains of these icebreakers, and they're like, you're welcome to come along anytime you want. You can't tell us where to go, but we're happy to take you out there. And there might be some things that we could do. I know that there's work being done, good work at Bowling Green State in Lake Erie, looking at algal growth under ice. As far as autonomous vehicles are concerned, we do actually have an autonomous vehicle in our lab, but it is not for use under the ice at this stage. There are many degrees of complication as soon as you can't come to the surface to get locations and communicate and stuff like that. So I would love to think that by the time I'm finished with my career, we will have stuff swimming around on its own under the ice. For now, we'll stick with the moorings. Go ahead. Oh boy, you know, this is one of these times that I wish Dan were here. Let me see, and the two data sets, most of the stuff, a remarkable amount of this stuff is available. So there's something for a very long time called the Great Lakes Ice Atlas, and that is hosted at the Great Lakes Environmental Research Lab in Ann Arbor. And there was some overlap here, and I think they compared relatively well. And now there's this thing called the ice mapping system, and I can find out for you. But Dan really would.
Ice mapping system, I know, but I'm just wondering, like, if it's that, like.
For this later data, yes, it was the ice mapping system. Yes.
Okay.
So.
So you compare it with winter air temperature, and I'm just wondering if you compare it directly with summer water temperature or duration of open water season.
So the metric we're using, duration is a really weird thing because if you have a little bit of ice for a long time, that's not as important as having a lot of ice for a short amount of time, right? And so we tend to use this, this metric, I guess it's here. Oh, no, it's neither one of those. The metric we use is this sort of conflation of both aerial coverage and duration, where we're averaging it over a specified season. Again, there's one slide in here with duration in it. I'm trying to think, like 2008 was actually, most of these years, even 2012, the ice duration, and I think we're defining duration by like, I think it's 5% coverage, and that number is sort of arbitrary. The results don't depend sensitively on the number, so it doesn't really matter. But 2012, you know, had maybe a third the ice duration of 2014, but when it comes to the impact of that ice, there's no comparison, right? And so duration in and of itself ends up not being necessarily a very useful measure. Most of this ice in 2012 is going to be in Chequamegon Bay or Whitefish Bay, these shallow fringing areas, rather than in the open portion of the lake. Is that?
So it means the ice cover is starting of ice on the lake, not completely ice.
That's right. That's right. Yeah. Most in 9 years out of 10 and 19 years out of 20, we don't get complete ice coverage on Lake Superior, right?
But you have a percentage of definition, like 5%.
That's right. We use some, and again, you can sit and test to see whether your results are sensitive. Anytime you make an arbitrary choice like that, you should check to see whether it affects your results. In this case, if you use 6 or 10% or 2%, it doesn't really make any difference. So I am thinking of two things right now. One is that we have another paper I didn't talk about here where we actually came up with a proxy to use that Sault Ste. Marie data which is this amazing, well-resolved data set at this power plant, to predict water temperature in the open lake. And so Sault Ste. Marie is downstream of Whitefish Bay, which is this big, broad, shallow bay that the lake drains through. And of course, it's in a river. And so you could legitimately ask, is that really representative of what's going on in the lake? And we showed that it's complicated, but you can do it. And there's a weird hysteresis, and there's a lot of corrections you have to do. But the point is, we were able to put together a 100-year temperature proxy for the lake using that time series. You're right, we could think about using air temperature. We'd have to think carefully about how to choose it to make estimates of ice cover. Another thing, and this is a fun story and marginally related to what you're talking about, but it's a fun story. There's a high school student down in Bayfield, which is in Wisconsin near where we are. There's a ferry that runs from Bayfield out to Madeline Island in the Apostle Islands. And he went back through old newspaper records to see when in the winter the ferry stopped running because there was too much ice, and when in the spring the ferry started running again. And you have to correct for hull construction and stuff like that. But what he showed is that the season of ferry operability over the last 100 years has increased in a statistically significant fashion, which is a really sort of cool way. I find it fascinating trying to come up with ways of thinking about what happened in the past, right? And that was a really clever way to get at it. I like to say that we can put a temperature sensor anywhere in the lake we want, but we can't put a temperature sensor in the lake any time that we want. We can't put a temperature sensor in the lake 50 years ago. So we have to look around for proxies like that. It might be interesting to see whether years like 2014 have occurred before in some sense. So one thing, well, cold is not necessarily bad for fish, right? I mean, and ice actually forms a protective barrier for some species where you need that ice to protect against predation. And I don't understand the details of that. One thing I pointed out, though, is you couldn't ask. I mean, when we design an experiment in the lab and we have a control variable, we run it over a wide range, a wide dynamic range. You couldn't ask for a better experiment right now than 2012 and 2014 happening right after each other, or right next to each other. And so I pointed out that if we don't see, and fish have year class. Fish spawn at a particular time of the year, and so there are fish that our ages are continuously distributed. Fish have very discrete ages because they spawn at a particular time of the year. If we don't see a difference between year class 2012 fish and year class 2014 fish, then we're probably barking up the wrong tree. I mean, this is just a really fantastic range. And I haven't really seen a lot so far. And people point out that year 2012 fish were there in 2014 as well. And so there's an integrative effect. But when it comes to a behavior like spawning or surviving your first year, if there's a climate impact, if we expect a climate impact, we should be able to see it with just a few years of data here. We have done, Dan, I should say, when I say we, I mean Dan, have done a lot of work at looking at whether there are optimal ranges. And it differs by lake. And so I wanted something that was really straightforward, so we just chose a big time chunk. But the answer is yes, it does. Let's see. Air temperature in December and January play an outsized role. So you can correlate, you can look at a time series of ice coverage and correlate that with monthly temperature anomalies. And the correlations in December and January are very high. November sort of makes a difference. October makes no difference whatsoever, which is really interesting. It says that up until October, nothing that happens makes any difference to the ice coverage. November makes a little bit of it. December and January, really the whole game.
Is that about how, like, if it happens in October, it might get warm enough again to melt any ice you made?
I think that, yeah, there are also issues with the fact that a lot of that cooling is going into that, I'm sorry, not the cooling, the mixing is going into stirring away that upper layer. The question is generally about what maybe some of the physical processes towards ice formation are. If you look at If you look at plots like this, these temperatures, and we have thermistors as close as 10 meters to the surface, which sounds like a really long distance, but the temperature is really very, very uniform over the top 60 to 80 meters. They're getting down, they're not getting to 0. They're getting to about, again, 0.1, and I don't know what the significance of that is. Typically, if you add solutes to water, it lowers the freezing temperature. So that ice freezing mechanism is happening right at the surface. There's not a field of ice crystals being formed over the top 60 or 80 meters. It's something that's going on right at the surface where the lake is simply unable at that stage to continue cooling off the water below it. Or, for that matter, mixing that cold water deeper and deeper. So
You also go from like a change in albedo appears with the ice.
so that's the thing is that albedo change, or in other words, the brightness, the reflectivity of the ice, is this real step change.
Yeah.
You're going from open water is like 93% of the light that hits open water gets absorbed. 40% of the light that hits ice gets absorbed, and the other 60% just bounce back out into space. So yeah, so there's a really strong nonlinearity involved in that ice formation process as well, which makes it all the more complicated. Okay.
I propose, if there are any more questions, take it offline because we're running out of time.
Okay.
Let's give Jay another hand of applause. Thank you very, very much.
Thank you.
I have a small